introduce Cumrun Vafa from Harvard, who's going to speak about Feynman graphs and Calabi-Yau Threefolds.
Thank you. It's a great pleasure to be here and give a talk in honor of Blaine's 70th birthday. I'm going to talk about a number of topics, but basically all centered around some recent work I've done with a number of collaborators. So basically some background is needed to give the basic setup. In physics, we're interested in objects we encounter in any form we have, but in non-supersymmetric theories, in general quantum field theories, the objects that we encounter end up being generically unstable. So we have particles, they decay away, and typically we don't have stable particles around, and sometimes we have some extra symmetries which allows us to have some stable particles. In the context of supersymmetric quantum field theory, stable particles are much more canonical in some sense, and they end up being related to what we call BPS states. The spectrum of these states end up being related to accounting for example, for the entropy of black holes in supersymmetric quantum field theory, the supergravities, and the like. And so the understanding of these BPS states, or what you could think about as stable particles in this theory, is a crucial thing for us, and in some sense is the backbone of these theories. So in some sense you have a way to think about these theories in terms of identifying a blueprint of them in the form of what are the BPS states, or what are these stable particles. That gets translated mathematically to studying calibrated cycles. So if you're interested in understanding the spectrum of these particles, you might as well ask, what is the spectrum of calibrated cycles? And that's something that I chose to talk about, which is, of course, greatly influenced by Blaine's work, and so I thought it was appropriate. And it turns out actually it's a topic I have been also interested over many years, and in particular in the past few months myself, so it's very appropriate to talk about it in this context. And so what do we mean by stable particles and these calibrated cycles? As you recall, in string theory we have a dimension which is more than 4 space-time dimensions. So we have some extra dimensions which we have to decide what they are, and usually there are some curved manifolds like Calabi-Yau or the like. And on these, in these manifolds, we have some interesting cycles which are supersymmetric. Supersymmetric, and they satisfy nice properties, and these would be thought of as calibrated cycles. And what we do is we take objects which you can think about embedded in these subcycles, subspaces. So we take an object we call, let's say it is K, as part of this internal space M. So you take a subspace of M, K, and actually you put a point in the space, and you think about this as a particle at the point P, where this is representing this object. So we say the BPS particle in the uncompactified space corresponds to a calibrated cycle upstairs. And so then there's a map. So once you give me a calibrated cycle, you basically give me a particle. And they're stable because they're minimal energy or minimal volume in that class, and they don't have anywhere to go, so they kind of stay there. So they're relatively canonical. Now, of course, understanding the spectrum of this is by no means trivial, because well, if they're isolated and rigid things, sometimes you can count them and just say they're 1, 2, and so forth. But often they come in families, and you have to understand how you deal out of that family a particle. So studying that is non-trivial subject. Understanding precisely what that family is and how you quantize the space, which means what is the cohomology of the marginalized space of these calibrated cycles. You have to quantize means finding the cohomology on these marginalized space, and then sometimes there's actions on these cohomologies of various types. You have to understand them, and they translate to physical properties of these particles. So it's a very non-trivial setup. Now there are many different types of these calibrated geometries, depending on which manifold we consider. 2 particular cases that have been extensively studied, actually to different extents, extensive studies, especially the concept of Calabi-Yau Threefolds, are holomorphic cycles and special Lagrangian submanifolds, which will be the focus of my talk, especially the holomorphic cycles. And also in the context of G-topological manifold, the associative and class-associative cycles. we have the spectrum of these stable particles. They are wrapped around different cycles in the Calabi-Yau. And we do something nasty to them. We squeeze them to zero. We squeeze them away. Now, why do we do that? So it turns out that the interesting quantum field theories, which we call infrared fixed points in physics, or conformal theories, arise by shrinking cycles inside this internal geometry. And together with that shrinking goes away all these nice calibrated cycles that we have all squeezed to zero size. So you used to have, so if you blow up away from the singularity, you have all these tower of different kinds of calibrated cycles, or BPS particles, and you squeeze them all to zero, and suddenly at that singular point, you have infinitely many of these cycles collapsing, vanishing to zero size. And this turns out to be a point of interest for physics. This corresponds to conformal field theories in physics. So these kinds of singular events in which infinitely many kinds of things potentially can squeeze to zero turn out to be extremely interesting quantum field theories. And they give us these massless modes which involve these interactions. And these massless modes are precisely made up, in a sense, of these objects which used to be these BPS states, or these calibrated cycles, which particles wrap around calibrated cycles. And so basically the lesson we learned is that singularities of the internal geometry, when you vanish these cycles, corresponds to conformal field theories on the leftover space. So they use, on the space that's not compact, they correspond to particles which are now becoming massless. In other words, if you think about the relation between the mass of these BPS states, since they are, you can think about these as kind of membranes, which are wrapping around the internal geometry, around these calibrated cycles, and membrane has a tension, so you basically multiply the tension by the volume to get the mass. Now, so in other words, the mass is proportional to the volume of these cycles, and as the volume goes to zero, you get these massless particles. So you have infinitely many massless particles interacting in a complicated way, somehow dictated by the geometry upstairs. So then it comes to life. These objects come to life. And why are we interested in making them massless? Well, the reason we're interested in massless things is because the correlation functions of massless things survive to infinite distance. They don't fall off. Massive things fall off exponentially, so the massless ones are the ones which actually survive, and they're interesting fixed points which have nice, large, long-distance behavior, what we call infrared fixed points. So having masses is very interesting and very important, and that's why we usually like to have massless particles in the game. And so these correspond to the membranes wrapped around these cycles. We are interested in this massless limit, as I mentioned, for physics reasons. We are interested in the singular regime. But nevertheless, we can ask whether or not the knowledge of the spectrum of these BPS particles away from this singular point can it in some way characterize that theory at the end? That's the question. And in fact, the conventional wisdom suggests that's the case. That is, the conventional wisdom suggests that if I give you a spectrum of these, if I give you a spectrum of these BPS particles, then there's unique theory associated with it. In other words, we don't have two different examples of two inequivalent quantum field theories, supersymmetric quantum field theories, which end up having exactly the same spectrum. So that means somehow they're faithful, that if we just give you the BPS spectrum, we can reconstruct back the original theory they come from. That has not been achieved yet, but that's at least a conventional wisdom, at least it's a hope, and in many cases seem to be consistent with this picture that they are as rich as the original theory. Now, this view actually is very different from the usual view in physics. In physics, we usually take a different view. We start with short distance physics. We write down a Lagrangian, which is describing the short distance interactions. And then we ask, what do you get at large distances? What is the spectrum of particles? And so forth. We don't usually ask the inverse question. If I give you the spectrum of particles at large distances, can you tell me where they came from? That we usually think, in the context of general quantum field theories, that you lose information by going to large distances. So that's the usual view, that if you start with a higher degrees of freedom in the conformal theory, flowing down you lose information, and therefore there's no way, in principle, you can reconstruct it. However, in the context of supersymmetric quantum field theory, that's not entirely true. That is, the knowledge of having these supersymmetric entities is sufficiently strong to tell you where they come from. At least we don't have any counterexample where you have two different supersymmetric quantum field theories giving you the same identical spectrum if you have enough supersymmetry. But then we really have to understand the spectrum of these BPS states. So the first question is, can we actually find their spectrum? What is the spectrum of these BPS states? And then, secondly, different manifolds can be connected by crossing through singularities. So I told you start with the geometry, and you shrink some cycles, but then there could be another manifold, totally distinct, and then you shrink it, and then they become the same manifold at the singular point, because you cannot distinguish them. In fact, geometric transitions usually go through such things. You have a singularity, and then you go from one geometry to one topology to another, so you can kind of tunnel through them. So you will have two different looking manifolds, really, topologically distinct, and they will definitely have different BPS states in them. They will have different calibrated objects in them. So how could I possibly claim that the property at that singular point is characterized completely by these BPS states when they're different? Okay, so that's the question is, how could it be that even though we can have different manifolds, they will have different geometry calibrated cycles and so forth. Nevertheless, I claim that characterizes these theories. So that's what I need to explain. Of course, there's no contradiction with saying they give the same theories, because we could start with a given theory and go in two different directions and get different BPS spectrum. My statement was that a given BPS spectrum cannot come from two distinct theories, not that a given theory cannot go to different BPS states. So that's not a contradiction with what I originally said, but it's a subtlety here. And we will need, if we claim that you can reconstruct back the original theory from the BPS spectrum, I have to give you a way that even out of this different looking BPS spectrum, I can get nevertheless the same theory back. So that's the second subtlety that we need to understand. So first I will spend quite a bit of time to try to actually go over how we actually go about computing these spectrum. That's already a long and interesting story that I think is interesting to recollect, and I will do that. And that will be relevant anyhow for what I want to do for the second step, which is how do you actually argue that they will actually lead back to the same data. So the case that I'm going to focus is a special class of physical theories related to Calabi-Yau Threefolds. So, and in fact, we consider a situation where you have, in the physics context, the M theory, 11-dimensional theory, where you take a space to be a product of a 5-dimensional space times a Calabi-Yau threefold. 6 plus 5 is 11. That's the way I split my space. And Calabi-Yau threefold, the particular singularities that I will consider are when you have 4 cycles and then shrinking to 0 size. So I'm interested in geometries involving Calabi-Yau, where 4 cycles shrink to 9. These turn out, we believe, to lead to 5-dimensional conformal field theories. 5-dimensional superconformal field theories with minimal number of supersymmetries. So this gives you a way to construct in 5 dimensions a huge number of possible new quantum field theories that we otherwise don't know how to study, because we don't have a nice generalizable Lagrangian. But nevertheless, from the arguments of string theory, we do expect that these actually make sense. For example, a simple example is the following. Look at the local, suppose you have a Calabi-Yau with the singularity of the form C3 mod Z3, where you take C3 to be just identify Z1, Z2, Z3, and then Z3 acts by third groups of unity acting on the 3 coordinates. This is singular, this space is singular, and you can resolve the singularity and you blow up the point to P2 with an O-3 bundle over it, and this is a resolution, which is could be a local part of the Calabi-Yau. As I said, I'm interested in shrinking the 4 cycle, which is, in this case, leads you back to C3 mod Z3, which is you take P2 and you shrink it to nothing. So this exemplifies the kind of classes of theories I would be interested in talking about. What am I doing here? I have a P2 which is shrinking to nothing. And what are these BPS states? Well, in this case, they are holomorphic cycles, and in this case, holomorphic curves. So you're interested in actually understanding the structure, the spectrum of these holomorphic curves. For any given genus, you can not find not only one, but typically a huge family, some dimensional family, depending on the genus, in the P2. And you'll have to find the cohomology of this moduli space. More precisely, it's not just the cohomology of these curves, but cohomology of this curve with some extra data which has to do with the line bound which lives on. So this is what we call D-branes, or in the M theory, the M2, the analog of it is for M2 brane. There's anyhow some convolution needs to be done. And so the BPS spectrum ends up to be, in some sense, counting this as these curves, which is studying more precisely the cohomology of the corresponding moduli space. You can imagine that this is a complicated story, because even though we can write down a curve of a given degree or a given genus for P2, try to find the whole family, study the cohomology of that moduli space is not entirely trivial. It turns out that studying Gromov-Witten invariance for this theory, or what in physics we call topological strains, leads to the BPS spectrum in this kind of theory. So this requires knowing the relation between how you get the BPS integer, BPS states from the Gromov-Witten invariants which are rational. So you want some integral data associated with these rational data that the Gromov-Witten computes. So there's a dictionary for that, and the basic formula is the following. So if you look at if you take the generating function of all these Gromov-Witten invariants and put them, stack them together, exponentiate them, I'm calling that Z of Gromov-Witten, you get a product in this form, which basically is follows. You consider a degree of a curve in this P2. For every degree, you can imagine that you have this curve in that particular degree in P2. But when you study that cohomology space of that degree D curve, it turns out there's an SU2 times SU2 action, which generalizes the usual SL2 action on the cohomologies. So you have SU2 times SU2 action. You can decompose this cohomology accordingly. And according to that, you will get a set of integers, which is basically the dimension of these cohomologies, for that degree, for that particular Si and Sj, which correspond to the corresponding character elements of the two SU2s. So you have an object which is basically the spectrum ultimately of what we want to count, ND, Si, Sj. And it turns out that the partition function of the Gromov-Witten theory can be written as a product in this form, where T can be viewed as identified with the Kähler class of the P2. This multiplies the degree here, E2 minus D times T. And the Qs can be identified with the exponential of the genus counting parameter, or what we call the topological string coupling constant, lambda. Here we have actually a refinement of it, which is there are two different Qs here. In the unrefined case, you identify both of them with one parameter, so you lose some information. So there's a reduced information when out of these two integers, you only keep track of one of them. And that's the usual topological string. So the usual Gromov-Witten invariance identifies them to one parameter, but you can actually refine them, and you can talk about this object, which depends on two parameters, the refinement of it. You take this product over all integers from 1 to infinity and d1 to infinity and so on. So you basically get all of these raised to the power of these integers. So this infinite product is the topological string or the Gromov-Witten partition function. So if we know that, we can read off these integers, n's. So the ultimate goal here of understanding these n's is the same in this case to understanding the partition function of topological string, or more precisely, what I mean by the refined one, where you have these refinements where you can actually get more information.
Can you recall what the SU2 plus SU2 action is?
Yes, it has to do with the following. The diagonal piece of it is the usual SL2 acting on the Kähler. If you have a Kähler cohomology, you have the usual SL2. That's the diagonal. But then there's a further splitting having to do with the fact that we look at line bundles on top of this. So there's a natural Jacobian having to do that genus. And that SL2 keeps track of the breaking up according to this vibration. That's the others. So that's the answer. So we are interested in this. So if we now we have to see how you actually go about computing this, and then that's equivalent to computing these. Well, it's a long story, but I basically say what it boils down to. It boils down to computing the topological vertex formalism. And this was actually developed based on the relation between the topological strings, Chern-Simons theory, and Lagrangian duality. So there are various ingredients came into actually giving a solution to this problem of how you actually compute these guys. And I will be focusing on toric Calabi-Yau threefolds. This is a large class of singularities of Calabi-Yau threefold, which is quite rich, and that's going to be my focus. So I'm going to explain how, in the context of Calabi-Yau threefold toric, what is the formalism which actually ends up computing this chromatin invariance and ultimately, therefore, the BPS spectrum of interest for us. So sorry for this. I'm going back to toric geometry. I'm not. I think probably this is well known to everybody here, but still, I want to make sure we know the object we're dealing with. So start with the complex plane, and there's an natural Kähler form on it. And I want to think about this in the usual form as the absolute value of z squared raised to theta. And therefore, I want to think about this naturally as a symplectic space, where I split up my symplectic space into the z squared direction and the angular direction, the circle. So in this way, we think about the complex plane as a half line, given by the z squared, and the circle shrinking at the origin there. So sometimes we just draw half of this space, maybe just the red line, and we remember that there's a circle on top of each point. And whenever the space ends, we remember that that circle has shrunk to nothing. So that's the kind of map between the complex plane here and this toric picture, which is just a semi-line, semi-infinite line. Similarly, for the case of C2, the same picture. Now, it's just I do the same for each C1, so I just basically get first the quadrant in the R2. That corresponds to Z1 squared and Z2 squared. On top of each point, I have a torus. The torus shrinks to a circle line as you restrict each of these two lines, and shrinks to nothing if you go to that point. So clearly, we can generalize. But I do all this to get to here, which is a C3 case. It doesn't take too much imagination, I would think, to think this C3 generalization is certainly this. So you can think about this as kind of like a corner of a room somewhere, at least two coordinates. And I want you to think about it slightly differently. I want you to think about this looking like a cubic graph. So this is a cubic graph. Namely, there's a point there and there's three lines emanating. So it's like a trivalent vertex. This is not the way we usually think about C3, but I want to emphasize that's going to be relevant. So thinking about, so I could not have done this if I didn't go to C3. So in other words, if I stop with C2, I wouldn't have a vertex. So the first time I get a vertex is in dimension 3. Okay, so we're getting some kind of vertex here, which is quite bizarre if you wish. You wouldn't think that naturally like that in the math language, but it's going to be crucial for what I want to say. So we get these kind of, then we can actually think about these pieces of this toric geometry. So basically each corner is like a C3, but we can glue them together and get more interesting geometries. And here we have a bookkeeping device where you can actually make sure to orient these lines that you draw. You can actually project everything down to a plane, actually, and draw the lines whose slope keep track of which cycle out of the corresponding tori strings. So there's a meaning to drawing these. You actually orient these according to the slopes. Their slopes will be rational, and they will tell you, according to those slopes, which particular cycle of the toric geometry shrinks. So
orient the tripod.
You orient them, but also the
Tripod.
That's right. So you orient them. There's a particular direction, which is this diagonal direction. So you project down in that direction. So you have a projection down to the R2. We're interested in Calabi-Yau threefold, where that particular one is trivial. And you look at the particular other cycles which are shrinking on each cycle. And so that's and the data of which particular cycle shrinks you do according to the slopes of these guys. So there's a T2 basically that's going to be relevant for the shrinking, and that corresponds to the slopes of these lines. So this picture I'm drawing here looks like...
I got lost.
You got lost.
The lines.
So basically the relevant piece is going to be a T2 inside this T2 that's going to be shrinking. So in the T2 has a homology, first homology. So the P comma Q homology is like a P comma Q slope. So you orient these lines to the PQ directions in R2, which corresponds to the corresponding cycle shrinking. So this data of the slopes here will tell you some data about the toric geometry itself. It's not just, I'm just drawing random lines. Geometric positions, exactly. Exactly. So it's not just the graph itself, but actually, metrically it makes sense, and the direction and so on makes it Euclidean geometry you have to draw very carefully. But actually it's more than that. So you can actually now use this to actually construct these geometries where you have these two different corners of C3, which are now two different patches of the C3 geometry, and you can get non-trivial geometries. For example, you can get a geometry, in this case, O minus 1 plus O minus 1 over P1. So this geometry over here, you can immediately spot the P1 here because each half line, as you recall, is a circle which shrinks at each point. And so here you have the circle shrinking at both ends. Of course, it gives you a sphere. So this intermediate line in the middle is a two-sphere. And these two directions are the two non-compact directions, which basically correspond to the O minus 1 plus O minus 1 direction of P1. And so this is a nice way to capture this non-compact Calabi-Yau threefold, this toric threefold, which is the total space of O minus 1 plus O minus 1 bundle over P1. The nice thing about this is that in the physics context, there's actually a dual description where these objects literally are, you put, it's not just a mnemonic, but actually you put what we call the PQ5 branes, which you put them in that exact location in order to capture the dual description of the same Calabi-Yau. So string dualities brings this to life, basically. Namely, it says that you can literally construct them by putting objects along those lines in these particular angles, and the condition that they glue nicely and so forth has to do with the fact that there's no tension at the point, that they're balanced, the forces at each vertex get balanced. So it's a very beautiful geometric description that matches beautifully the toric geometry. And so this is a simple example here. Or you can do things like flops. So this is very nice. You can bring these two together, shrink the P1 to 0, and go the other way. And this corresponds to just doing the flop. When you have a singular, when you go down, there are two different resolutions of it you can have. One is the other one, and one is the flop version. So you can easily see these geometries coming to life again in these kind of toric pictures. So the example I told you about, the C3 mod Z3, also has this nice toric description. Namely, you have, you can take basically three patches of C3, and these three patches of C3 can be viewed as three different patches of P2. In a ratio of which you can actually describe the total space of an O minus 3 bundle over P2. The triangle piece, the interior triangle, can be viewed as P2 with a T, so you can think about P2 as a triangle times a T2 roughly, where different cycles vanish different places. And here you have one extra direction because there's a Calabi-Yau threefold, which makes it the O minus 3 bundle over P2. Okay, so again, these angles and directions and all that are very specific, and I'm not, it shouldn't be viewed, I'm just drawing a triangle with lines, but they're very specific directions and so forth, but I'm not bothering to say it here. Those loops correspond to 4 cycles. So for example, here I'm describing a different geometry. Here I have a P1 in this direction, and another P1 in that direction. So this geometry is the geometry of P1 times P1. You have two P1s. And then there's non-compact direction, which is the line bundle O minus 2, comma minus 2 over P1 times P1. Of course, the choice of the bundle is obvious by the condition that the first term class should vanish. So that dictates what is the bundle on top. In all of these cases, we're talking about Calabi-Yau threefold, which have vanished in first term class. So this is a geometry associated to O minus 2, comma minus 2. And notice that you now have a closed cycle in this geometry, which has to do with the fact that there's a 4 cycle suddenly, P1 times P1. You have a compact 4 cycle now. And that relates to this loop. You can also do blow-ups. For example, if you take that triangle and blow up 2 points, each block corresponds to creating this P1. So this one and this one can be viewed as the two blown up points. So this is the blown up geometry of P1, of P2, sorry, at 2 points. So the nice thing about this is, again, that these graphs and so forth are actually grains and you can move them around and so forth, but they also have a simple mathematical explanation. So there's a nice match between the corresponding physics and the math picture. You can do much more complicated stuff. You can begin to build up all these graphs with each other, and you can describe much more complicated geometry, which are not easy to describe in words, but actually very easy to describe in graphs. So this is beginning to look like another Calabi-Yau, which has 2 4 cycles. Now you can see this 4 cycle and this 4 cycle. You can immediately count the obvious P1s or curves here. These are basically edges. But of course, you can have much more fancy things. For example, you can have edges, curves which are actually going in the middle somewhere, and so forth. So it's going to be not just the obvious curves that you get, there's going to be a much more interesting spectrum. For example, in the case of P2, clearly there will be many, many curves. We know at each degree there's a curve, and it's a family of them, and so forth. There's a complicated story, even in this case, to understand the counting in that story. You can have much more complicated looking ones. I'm just trying to be artistic here, not very artistic. I'm trying to say you can have more complicated things. But we are interested in the case where the 4 cycles shrink ultimately. And when they shrink, they all look like some external lines coming together to a point. In fact, you can imagine having a situation where you have all these different 4 cycles and all these different complicated things, and you squeeze life out of all of them to nothing. And what you end up getting is just a number of just external lines coming together at one point. This is beginning to look like a diagram, kind of diagram physicists like to draw for scattering diagrams. And you have a bunch of particles, and something happens in the middle there. Okay, so we have some kind of a scattering going on. Of course, we then open it up, and then we look around, and we have these 4 cycles, and then these things come to life, but we can close it back down. That's our conformal point. So this is the singular Calabi-Yau. All look very unremarkable. They're just a bunch of lines whose slopes are, of course, important. Exactly which slopes characterize the conformal theory. So choosing precisely which slopes and what degeneracies you have will characterize what is that conformal theory. But you just, ultimately the picture looks a little bit boring looking. Now, the toric diagrams, as I've tried to explain, have remarkable resemblances to a cubic field theory. They look like Feynman diagrams. So we have these edges. We usually put some propagators, we put some labels. In the usual case of Feynman diagram, we put momentum. So we put some label on each edge. And for the second element in Feynman diagram is a rule. For each vertex, you put some interaction. So in this case, you have alpha, beta, and gamma. If they label whatever label you have on the edge, you have to give the interaction between them in terms of some coefficient, which depends on alpha, beta, and gamma. And then you also integrate over the internal loops. Okay, so this is what we would expect for a Feynman-like diagrams and situations. And I'm about to tell you that the way we compute normal within invariance for these Calabi-Yau threefolds includes the first 2 elements. That is, we will have to associate a propagator and a vertex. And then using that, we can actually write down the answer for normal within invariance for all these toric Calabi-Yaus. So what is the analog of the propagator? Well, you take a line, and the length now actually means something. The length of this line is the integral of the Kähler class of the corresponding P1. So that's the Kähler class, which is geometrically relevant, and we call it T here. So you take the length T. This is sometimes in physics we call it Schrödinger time. So there's a length associated with that, the Kähler parameter. And for every edge, we associate a 2D partition or a Young diagram, alpha. So you put for each one of them you put the label alpha, and such a thing carries a weight, e to the minus t times the number of boxes in that Young diagram. So in other words, the edges are labeled by 2D partitions, and you basically multiply it by e to the minus the length times the number of boxes. That's the propagator. three partitions, three Young diagrams, and I'm supposed to associate to them an interaction, like Feynman diagram, with something which in this case depends on the coupling constant of the theory. And this Q is exponential of the lambda, where lambda was the string coupling constant. So the genus counting parameter, the parameter which counts the genus in the Groningen theory, is related to this Q by e to the lambda. Q is e to the lambda. So there will be some object I have to associate to these interactions. What is it? Well, if the alpha, beta, and gamma are trivial representations, the answer is very simple. All you do is you basically look at basically removing points out of integral lattice in R3, and you count how many consistent ways are there of taking them in some particular, what's called a 3D partition, with particular boundary conditions which are nothing at the end, and you just count them. That would be the case where they would be trivial. More generally, if you fix Young diagrams, alpha, beta, and gamma at 3 ends, what you do is simply look at all the 3D partitions, which have to do with the ones which asymptote to diagrams which have a particular structure at the 3 ends. So here you see this Young diagram beta here, and gamma here, and this alpha up there. You look at all the 3D partitions which kind of asymptote to that, and just count how many such things there are. Well, then you count how many boxes you basically have put here, and that n is the total number of boxes, and you sum over all such possible configuration. That is the answer for the rule. That's the rule, the Feynman rule, if you wish, for this cubic vertex. There's a refinement of this, and that I won't talk about, but basically you can kind of refine this with a two-parameter version involving Q1 and Q2, which allows you to compute the more refined version. So just to give you an example, suppose you're interested in computing the Groningen invariant for P1 times P1. You put labels on the internal edges, alpha, beta, gamma, and delta, which are these Young diagrams. And for each one of them, you put one of these partitions, these cubic interactions. In this case, you have alpha and beta Young diagram, but no Young diagram here. I call it empty. So you get C alpha, beta empty, C beta, gamma empty, and so on. So you get basically 4 vertices coming for the 4 vertices of this square. And you multiply it by e to the minus the Kähler class of these two P1s. I'm calling the Kähler class of the P1s by T1 and T2. So e to the minus T1 times the number of boxes here, e to the minus T2 times the number of boxes there, and so forth. So it's very simple. That is the answer. You sum over all alpha, beta, gamma, and delta. Then you have computed the Groningen invariance for P1 times P1. And therefore, you have computed the full BPS spectrum of this theory on P1 times P1 with all these possible degree curves sitting inside P1 times P1, all captured in this simple way in terms of these diagrams. It's remarkable. It's
one diagram.
One diagram. One diagram, but you have to sum over all these internal labels. This kind of structure we already were aware of. I mean, we discovered it like, I don't know, about 10 years ago or so, but so the resemblance to Feynman diagrams couldn't have been, I mean, we couldn't be avoided, it was obvious, but there was something missing in this picture. In Feynman diagrams, we also integrate over the loops. Here we're not doing that, we're just keeping it fixed. It was a bit unfortunate. The symmetry was so much there, you would really love to integrate. You want to do this integration with the loop, and it wasn't there.
Well,
very
you
frustrating.
do this ill-defined thing, right?
Sorry?
You want to do this ill-defined thing.
We want to do this ill-defined thing. Sorry, ill-defined is, physicists don't have a problem with ill-defined things. We have a problem with unmotivated things. We weren't motivated. We didn't know what it would mean, what would I be doing. We would make sense out of it if it made sense.
Right.
If it was good for something. That was not our issue. And that's the issue that you guys have to make.
I was joking.
I know.
So Cumrun, in your big three-dimensional box inside of which you were going to count these configurations,
Yes.
How big is the box?
No, the box is infinite. I was just drawing, this is just my limitation of the space. So you think about literally, it's 3D partitions, basically the same kind of diagrams you have for the Young diagrams, you have a 3D analog of it. But these diagrams would asymptote to particular Young diagrams at 3 edges at infinity. And just sprinkle the boxes which get arbitrary numbers, so you can have arbitrary number, and so you can have bigger and bigger series in cube.
Yeah, the exponential rate.
These are the exactly. These are the alpha, beta, and gamma are the boundary conditional of 3D partition. That's all they are.
There's an infinite sum.
Infinite sum, yeah.
But exponentially decreasing ways because it's even the minus.
Exactly,
So it
exactly.
converges.
Exactly. Okay, so that's where we were. But before I get to the loop slide, I want to say, I want to go to the, give you a kind of a, in the middle what happens.
So is this like computing the BTS formula?
Exactly.
Of the other formula?
So this thing, when you write it down, it becomes a product formula, and you can read off these n's, the number of the so the given degree, and so on. It just all assembles into a simple group. Ultimately, it captures the whole answer.
This is a conjecture, though, right?
No, well, I would say by this time, I would say that mathematicians also have proven it, that this is actually the growth within, and the fact that it relates to these integers is, you could call it conjecture of mind with Comrun. Yes.
So this been checked in these cases?
But for all toric cases.
All toric?
Yeah. So this is, the fact that the grown within for toric cases, this I think is mathematical fact, I should say. I'm not giving references to who did it, but it's a statement. Okay. Now, before I go to this loop integral, I want to say something about even the first of these elements. They actually have a much simpler description, or a slightly different description, if you use mirror symmetry. So if you use mirror symmetry, it turns out that you end up complete reformulation of what we just said. Namely, you introduce C star times C star space, which are parameterized by two variables x and p living in C star. And the relevant object in the mirror symmetry turns out that for each toric threefold is captured by a curve, f of x and p equal to 0 and C star times C star.
What does the curve capture?
It's like a mirror geometry to this toric threefold. More precisely, I can make this a threefold. Usually the mirror of a threefold is threefold by putting u times b here. So you can put a boring parameter here, which makes it look like a hypersurface in C star times C star times C times C. But basically the guts of it is this curve in C star times C star. So for example, if you're interested in the mirror for P1 times P1 geometry, the answer turns out to be a polynomial in this form, x plus 1 plus x inverse plus p inverse, with these parameters playing the role of the Kähler classes of the two P1s. And basically the rule is not that difficult to see. You put, for each point, for each region on this graph, you put a monomial, and you think about this as x on the p direction. So you put here you can take x1, x inverse, p1, p inverse, or the other way. And so these are the things, and then you can actually find what these rules mean in terms of the corresponding Kähler classes. So basically there's a very easy rule, in other words. Just by this toric geometry, you can figure out what the curve is. It's not a complicated thing. And what it ends up being is basically fattening up this graph. You just draw that graph and you promote it to a string diagram. So you just take this Feynman diagram to strings. That's what we always do in string theory. So we had even seen that. We'd seen that these Feynman diagrams, when you use mirror symmetry, become the usual fattening up of point particles to strings. So it looks like there's a string theory going on here, in fact. Again, except the fact that you still don't integrate over the shape of the string, or have a rigid string in the sky somewhere, and it's just there, and it depends on the P1 times P1 shapes and so forth, all things. But can we actually reformulate the whole computation of chromatin invariance? And it turns out that you can. Namely, it turns out that you have to introduce a non-commuted deformation of the space, where you declare x and p are not commuting variable, but they pick up a parameter q. If you take xp is not equal to px, but there's a q parameter, there's a q deformation of the space. And on this Riemann surface, f of x and p equal to 0, lives a fermion. What that means is a section of a split 1/2 bundle. You write this interaction, and you integrate out. You get the determinant of del bar. So the statement is, computation of this complicated-looking graph rules and all that I told you about, in this mere language boils down to computing the determinant of the del bar operator on a surface, which is actually, for which the fermions can be viewed as a module of this non-commutative space. As a module, the module. So basically, these x and p act on the parameters of the space as f of x and p is 0, but now this becomes a non-commutative f. So you have a non-commutative space in that sense, and the size are, this fermions represent the module. And you are basically computing the determinant of del bar acting on these elements.
D module in the sense of mathematics?
Yes, yes. This is a mathematical sense, yes. So the statement boils down to saying that, okay, all you're doing is you're coming in terms of the del bar operator in this Q-deform space. That is equal to the same thing I told you in the other language, the partition function of this theory. That's the mirror description yet of that same BPS counting. So I've given you two different ways of counting this BPS thing.
How do you know?
Sorry? How do we know? We have proven it in our ways.
What was singularity?
Sorry? This is surface f of x and this is the mirror surface. So that's f of x and p is 0. So for every toric threefold geometry we have, that was that curve.
Oh.
That's that curve. So you basically a fermion lives on it, and it would have given you a determinant of del bar operator except that it's non-committed. So that object gives you the answer for all of those geometries. Now we come to the punchline. So the similarity to Feynman diagram is striking. So we have Feynman rule, Feynman diagram like rules, and so forth. And the missing ingredients is that we don't seem to be integrating over the loop variables. We're just having it fixed.
It also fixed the same equal.
But there's more than that to this. So in other words, they look like you have some restrictions on the times and so forth. There are more differences, but the main difference is not that. The main difference is actually the fact that we don't integrate, and that's the more crucial one. So the question is how you actually come up with what is the meaning of this restriction and so forth. Well, it turns out that we were not asking the necessary question for which the answer would have forced us to integrate. So if you ask, what is the partition function of this theory, this five-dimensional theory that you get under M theory on this Calabi-Yau threefold, on S5 or S1 times S4, it turns out you have to get that object and integrate, it turns out. So we just weren't asking that question before. So you say, okay, fine, I want to compute the partition function. What do you do? The answer is you integrate. Now, let me explain exactly in what form. So what do I mean by integrate? So if what you have to do is you have to integrate over normalizable Kähler forms. So normalizable ones are the ones which correspond to fixing the asymptotic behavior of this toric diagram and having like these breathing modes for these loops. Those are the normalizable modes. So for example, O minus 3 over P2 has one normalizable mode corresponding to the size of the P2. So those are the degrees of freedom we're instructed to integrate. Or for example, in the case of P1 times P1, you have two Kähler classes here, T and T1, this one and that one, but there's only one integral you're doing because you have to fix these four asymptotic directions. So you're integrating in a correlated fashion where these sizes are not arbitrary, but they're correlated in this way. That if you want to integrate over this length is the same as that up to a shift. And you're just integrating over T prime. And so you end up doing an integral of the form dt and the partition function of this theory with Tn, T plus T prime, where these are the corresponding what I called T1 and T2 before. But now we're putting T1 here and T2, but we're integrating over a specific direction. Of course, we have to deal with what we mean by the integration as this thing, and we have made sense out of it, so I won't bother saying exactly what do I mean by this integration. So in the language of the mirror description, as I said, there's a string. What this means is that you're integrating over the Riemann surfaces, which have the fixed asymptotes. So you're basically looking at the curve in C star times C star. You're looking at fixed asymptotes, and you're just integrating over all possible curves in that class with those asymptotes, but you're allowing things locally to change in sign. And so that's the mirror description. So you're looking at the moduli of these curves with that restriction.
That curve had a lot more moduli than just this one.
Yes, it has much more moduli. In general, in genus G, you have 3G minus 3 moduli. In this case, there's not that many because the genus is 1. But
there's quite a few there.
Right. So in general, you're not integrating. So this is the difference. One difference with string theories. In string theory, we have we don't integrate. We integrate over 3G minus 3-dimensional modulus of complex structures. That's a space of maps on this. Here, you should think about this as embedded objects. That's the difference. So these are embedded objects. As embedded objects, you don't have a 3G minus 3-dimensional family. It's a smaller one. You have one per. Exactly. You have restricted subsets precisely because these are embedded objects and you have very restricted family, and that's what you're integrating. So now I come back to the question I was asking before, namely, you might have two different Calabi-Yaus which shrink to the same thing. Why is this integral good? Well, it better be the same, namely, the partition function of the Gromit theory for the P2 one at one point, or the flopped version of it, will be different. But it better be that after I integrate over the corresponding loop variable, the answers are the same. Otherwise, sorry?
Why?
Because they both compute a partition function of the singular one on a sphere. So if they're both, their claim to fame is that they're computing something for the singular one, they better be the same, otherwise it's a contradiction. So in other words, having different spectrums of BPS states is captured by the fact that Z is not equal to Z prime. So I go one way or the other, I have different answers. Out of these two answers, if you do the specific integral, you better get the same answer out. Otherwise, there's a contradiction. So this is a sense in which the BPS spectrum actually captures a property of the conformal theory. So having this infinite spectrum is actually capturing something specific for the conformal theory. Or even more intensive type of things would be things like this, where the answers after the integrations better be the same, and we have checked, and they are, as a non-trivial statement that we get the same conformal theory out. And that conformal theory is only characterized by these external lines on the directions at the end, nothing else. This integral can also be thought of as defining a new string theory in 4 dimensions, as I was just explaining. Namely, you think about C star times C star as a cotangent of T2. So you have and you think about T2 as your space, and the cotangent as your time. So it's like a signature 2, 2 space, where the 2-dimensional physical space is T2. And your strings wrap around the physical strings, spatial strings, wrapped around cycles of this torus. And the interaction of these strings are the usual Kähler-Pence diagram we have. But then I was associating these Young diagrams with these pairs of Pence, alpha, beta, and gamma, and that turns out to be related to the oscillation modes of the string. So the oscillation of the string is captured in the Fock space, or the hyperspace, by a Young diagram, and this is basically capturing for you the usual Young diagrams, the usual interactions that we put in string theory after all. So this is basically saying, oh, all you're doing is just doing the usual string theory with the usual string theory rules. Namely, you're just doing the pair of Pence decomposition, but with the restricted moduli integration, which is compatible with the asymptotic boundary condition for the string. So this defines a string theory propagating in a non-commutative space where there's this Q parameter in the game, which plays the role of the string coupling constant. So I hope I have given an impression of why I think the enumeration of calibrated cycles is a beautiful subject. And also, in addition, it provides a powerful tool in characterizing superconformal theories. This can be used to compute supersymmetric partition functions, and also this is an index-like object. That's the integral result of that integral, which does not depend on how you actually desingularize your space. So I'll stop here. Thank you.
That was the shortest hour talk I've ever been to.
So I never saw a special Lagrangian cycle in this story. Is there a way of...
Yes. Actually, there is.
Something analogous?
There is. Actually, I hit the way we actually derived this topological vertex involved special Lagrangian. And it has to do with the following. So we have this geometry. So this is the C3 geometry, nothing fancy. And then it turns out that you have to actually introduce a special Lagrangian, which is, these special Lagrangians are, for example, Joyce study, or maybe others, I'm not sure, which involves the non-compact special Lagrangians, which have the topology of S1 times R2 in this geometry. So those are well studied. And basically, we had a situation where we actually also put some other, so you actually made this into actually a 3-sphere. So you have S1 times R2, but they actually put something else on the other side to make it actually compact. So you have this Heegard decomposition of the 3-sphere, where you have only half of it, and the other half becomes a full 3-sphere. And studying these representations turns out to putting gauge groups here, branes here, the special Lagrangian branes, and you put Chern-Simons theory on it, and you study non-invariants for this theory, which originally led to the formulation of the topological vertex. So the topological vertex came precisely by studying special Lagrangians and putting branes on them and relating it to not-invariants and so forth led to the formula that I did not explain. I just said it came. That's where it comes.
There is a string with n equals 2 worldsheets supersymmetry that you studied with Oburi. So there's also a non-commutative version of this. Can you comment on any?
Well, it's tantalizing to think that there's a relation between this four-dimensional space, this string theory, and the one we studied with Oburi. They're equal to strings. That one includes also self-node geometries and integral structures. It smells like each other, but I don't have a clear picture of what's the relation between them. But I suspect there's a relation.
For your string, you don't know of an action.
No, I just told you what I know.
Are there any direct cuts in this final equals?
Good question. Whatever it is going to be subtle because unitarity cuts, so the physicality. So since there's two common, I believe it's a 2, 2 signature, the notion should be slightly thought out. I don't have a clear picture of what unitarity cuts means, but there must be.
What if you start with Calabi-Yau and cross it with a circle?
Yes.
And you form something G2?
Yes.
Is this story complicated?
Yes. In fact, G2 again was related to part of how this came arose. Basically, so the way we look at this special Lagrangian is that you think about this thing. If you put a special Lagrangian here, you can lift it up to a 7-dimensional G2 align manifold, where you have a circle fibration, where the circle degenerates over the special Lagrangian. And the objects that we studied, which led to this topological vertex, were the disks, which lift up the associative cycles on G2. So in fact, that's the picture we So these disks, which are holomorphic disks, which end on these special Lagrangians, lift to, in the upstairs on the G2, to the associative cycle. So there's rich story there. So I could go on and on. They're beautiful. They're all there. They're all beautifully there. I believe that Conan will talk about some other aspects of these G2 align manifolds and the associative cycles tomorrow. Oh, there
Just, how do you want to see the relation with the modeling of the B model?
Well, the remodeling of the B model. So that basically relates to larger dualities and the relation of that to matrix model. So basically it relates to large n. And so to the extent that you compute the topological vertex using large n duality transitions, they are related. So now you can write down, but you can do in fact
Large
better.
duality referred to as Tahoe, original Tahoe.
The original Tahoe idea applied to the context of Chern-Simons theory. You take large n Chern-Simons theory, apply the ideology of the truth, and you get the duality between Chern-Simons theory and the closed topological string or Grommelton theory on the result conical. That's that number. So indeed you can actually write it down, but actually you can relate it more directly to studying what we call the Kähler gravity on the mirror geometry. So that's what we described in my paper with Robert on it. So I exactly described it here.
You basically have the space-time Lagrangian for any string, right? Can you check if this?
Well, naively, it doesn't look like it. That's why I was hesitant to say yes, but naively it doesn't because that one has no oscillators. The oscillators cancel out. Here we have these oscillators in the game, but whether or not it's the way I'm writing the integral that gives the oscillator there's fundamental difference, I don't know. So naively you would say the answer is no. That's not related, but I can't be completely sure until there's. So naively the answer is no, but there might be some hidden relation that I don't want to be too fast.